about synchronization and bit error rate and how it is used in our project. Then we have Hugo Fu with us. He will tell you about equipment, what we use in our project, the methodologies, and all the processes that we done in our project. And at the end, you will have Marais with us. He will show you the results and explain how we achieved them. And it will be followed by discussion and conclusion at the end. So what this project is about? Well, this project is about adding digital data to your analog frequency modulation. We hear to FM radio every day, like we are hearing it since our childhood. So what we hear is basically FM radio. It is not digital. But what is happening now is that DAB is coming into the market. So currently, I'm sure nobody of you have listened to digital radio yet, but it is out there, and it is being penetrated into the market. Currently, only 5% of digital radio is out there. So what will happen is that after decades, 2 or 3 decades, digital radio will be in the market, and FM radio will go away. So we need to save FM radio. So let's see what are our goals of the project. Basically, our goal is that to save our old FM analog receivers and extend their lifetime, because once digital is in the market, FM will go away. So our goal is to save those old FM receivers. To do this, we have to study different digital modulation techniques that can coexist with existing analog FM. And to achieve this, we have to test the functionality, if it is feasible or not. And we did this in our project, and we'll show you the results in the result section. And if we do this right, we'll have 8.2 million FM receivers saved in Sweden only. This figure is for Sweden only. Basically, we are saving those 8.2 million FM receivers. So what is AFM? Stands for analog frequency modulation. And we are varying our frequency once we add a message to our carrier frequency. So I'll try to draw a picture for you. Let's see, this is our carrier. And we have a message here. That's called KC. Once we have this message modulated with the carrier, what will happen is that the output will look like this. So this is what we listen to in our radio. This is analog FM, what we listen to. But now we have to add digital here. So what we did in our project is that we used different modulation techniques to add this digital data. And we used some of the equipment available in the research laboratory. And to explain about those digital modulation techniques and how we did this, I would like to call Liam.
Okay, hello everyone. My name is Liam. I will introduce the theory part of our project. In the last 50 years, the analog signal analog modulation method has been widely used in all of the world. But nowadays, the most wireless transmission are digital because the limited spectrum of the channel. So, which means the main purpose of our modulation today has turned into squeezing the data into the least amount of a spectrum. And we have many digital modulation schemes, such as binary phase shifting, conjectural amplitude modulation, and pulse amplitude modulation. And for the pulse amplitude modulation, as you can see from here, here's the typical signal. It's a sine wave. And hence, is using for transmission the information by varying the voltage level, or we can call it amplitude, by its individual pulses and in time sequence, which means the signal has been sampled at a regular interval. Every samples have proportion to their different voltage levels. For example, if we implement a PAM4 system, it will take 2 bits at one time, and it will map the signal amplitude in 1/4 possible. It should be, for example, the possible level should be -3, -1, 1, -3 volts. The reason that we use PAM in our project is it's easy to follow, to combine those two different modulation methods together. As we can see from this graph, here is our FM frequency modulation signal. It's analog signal, and here is our PAM. We have 2 levels. This is level 1, and this is level 2. For the analog part, the frequency varies, but the amplitude is constant. And for the digital part, the amplitude varies, but the frequency doesn't change. Then we successful combine those 2 different modulation methods together. The next part I would like to talk about is the constellation diagram. It's so-called IQ diagram. In the digital field, as we can see, in the digital field, the IQ diagram is widely used because, as we can see from the graph, it displays the signal in 2 dimensions, which is in x dimensions, it extracts the cosine part of the signal, which is the real part, and in x dimensions, it expresses the sine part of the signal, which is the imaginary part. And for the next one, synchronization. It's a very important technology in digital communications. Because, for example, if we transmitting a signal through a channel, the time delay and the phase delay will appear because of the instrument vibrations or some preventable reasons. So therefore, we have to estimate the number of time parameters by the receiver part, so make the whole system synchronized. And the last part is the bit error rate, BER, which is the standard to quantify the reliability of the communication system. And we would use the BER in our result to test if it's good or not. Okay, that's my part. I will introduce Edward. G4, the methodology part.
Hello everyone, my name is Xu Fu, and I would like to introduce a little bit all the simulation, all the experiments we performed in our university research lab. And I'm going to introduce a couple of equipments we used in the project. And as you can see, this part is the transmitting part. It's vector signal generator and also transmitting antenna. With this part, we can successfully transmit the analog and the digital signal into the air. And then this part is receiving part. It is receiving antenna and signal analyzer, and then we can capture the signal we transmit, and later we can analyze in MATLAB. And here the frequency, like we transmit the frequency is 1 megahertz. So basically, if we have like commercial antenna, we can actually hear what we have a radio, we can actually hear the voice we transmit here. And yeah. And then here the structure of the experiment. The first of all, in the MATLAB program, we record the human voice as an analog signal, and later we're gonna use it in FM modulation. And also in the MATLAB we generate randomly digital sequence, which we know digital sequence is only the binary number 101 or 100. And but in our case, this 1 is represent the higher level of the amplitude, and then 0 represent the lower level of the amplitude. So I can make an example. Maybe it could be like 0.8 and then 0.3. This digital sequence is the same length as analog sequence, and then we multiply them together. That's how we implement PM and FM coexistence. But there's one technique for synchronization later for future decoding between 80,000 and 90,000. Inside of the digital data, we only put only once, and we multiply with the analog signal. This region will be the original part of the signal because multiply 1. And now we finish through the vector signal generator and then also transmitting antenna, and then I can say our signal successfully online. Here we all can recognize this FM radio, and we will tune up to the 1 megahertz. We can hear our human voice and also music. This part works as an analog receiver. And also here for the receiving antenna and then also signal analyzer, this part works as digital receiver. With all the information we capture on the air, and then we through and then in the end we analyze the signal the data in MATLAB program. And before I introduce, there's a gap for synchronized sequence. And for example, this is our received message. For the synchronization, because we have time delay and then phase delay, we need to know exactly the position we start decode, and then later we can match to the original data. And so this is the receiving data, and then this is the transmitting data, original data, and then we do the cross correlation between those two. We both know the property of the cross correlation is find the most likely, but which position is the most likely. So it should be, and it will be, the peak. This peak represents the position they are most likely, and then we should receive information to this position and then start decoding, and then we can match to our real data. And after synchronization, it's supposed to be the 2 level of signal. The higher level you represent 1, and the lower level you represent 0. And simply in the MATLAB we introduce a decision boundary. So the upper level and then we decode to 1. The lower level of signal decode to the 0. And I can say proudly we successfully recovered the data, the digital data. And then also the DER looks promising. Thank you very much. My part is finished. I will introduce my coworker. We introduce the next part.
Okay, hello everyone. I will present you the results of our project. And those are the test analog information. The one above is speech voice that we recorded, and the other is monotonic music file. Please notice the difference. We'll have some discussion on this later. And these are the results after resampling and putting information on the IQ diagram. By doing this, we actually define the level frame, and this will translate the digital adding and as well as the decoding process. Those with the two rings are the result of the combination of digital and analog. We have tried different levels. I think this one is 8/10, and this is 4/10. This could be explained here. The level, let's say this is level 10, and for example, this is level 8, and then for the ratio 4/10, it actually gives a large difference between those two levels. And this will affect the result of bit error rate later on. We'll have some discussion on there. And after transmission, this is a signal we got in the receive part. As you can see, it almost has the same shape as the one we sent. And somehow here, the rings order are blurred by noise. This is the reason for the error bits. And for the synchronization, we compare the one we received with the same signal by means of phase information. You can see those are before synchronization, those are after. And by shifting the received signal back to the original position, we give the right order to the decoding process. And to speak of the decoding process, we use this figure, the absolute value of received information, because in this figure we can clearly say there are two levels, and well, in most of the part. And we just put our decision boundary in ring here, for example, 4.6, and then we just give 1 to those values above and 0 to those below. This is a figure of different digital adding levels compared with the bit error rate. As we can see, for low ratio, we have a low bit error rate. This is easy to understand because the low ratio actually gives a big gap between those two levels, and it's easy to distinguish and decoding. But however, the bit error rate, the small ratio will also give a big distortion in analog information. And so we need to find a proper boundary. And as learned from signal processing course, we know that the midpoint here is a good choice. The received quality varies for different analog information. For example, for the speech voice, we can simply cut the points outside the range and to make the cycle. But for the music file, because it contains a lot of information, so this will destroy the music file. So instead of cut the points to push the points to the range by only change the amplitude information and remain the phase information. This we can remain the content of information by this way. And we have success adding the digital PM to analog FM with good quality of analog information and also a low bit error rate of digital information. And so I might say that we have just saved the analog receiver and people don't need to spend extra money